All right, guys, welcome back. So this is Unit 5, Analytical Applications of Differentiation. You'll find most of Unit 5 is going to talk about using derivatives in the context of a graph and how that we can find certain information about a graph using the first and second derivatives. So first up is the mean value theorem. So the mean value theorem states if y is equal to f of x is a continuous at every point in the closed interval a to b, differential at every point in the open interval a to b, there's at least one point C from A to B in which the instantaneous rate of change is equal to the mean rate of change. So the idea is it has to be a continuous and differentiable function. When they talk about closed intervals, they mean including the endpoints, whereas open intervals are not including the endpoints. So what this essentially says, assuming this function is continuous and differentiable everywhere in this bound, then if we find the average rate of change, which is your slope, your secant line, and we set that equal to the derivative, there should be a point where that's actually going to be equal to each other. Now, you have to always check to make sure your function is continuous and differentiable before this does apply. And also keep in mind, it only has to be continuous and differentiable in the interval. Like if we, for example, have a vertical asymptote at x equals 4, but our interval is only from 0 to 3, we're okay. It has to, if it doesn't exist inside the interval, then we can't apply the mean value theorem. So using the function f of x is negative x squared plus 3x plus 10, we're going to find the average rate of change and then the instantaneous rate of change equal to that. So essentially, this is asking for the mean value theorem without explicitly saying use the mean value theorem. So for part A, we want to find f of 6, which would be negative of 6 squared plus 3 times 6 plus 10, which is going to give us a negative 8. We want f of 2, which is negative of 2 squared plus 3 times 2 plus 10, which is going to give us positive 12. So our average rate of change is negative 8 minus 12 over 6 minus 2. Negative 20 over 4, we get an average rate of change of negative 5. So now for part B, they want to compare the instantaneous rate of change to this. Well, instantaneous rate of change is the derivative. So we take our derivative, f prime, would be negative 2x plus 3, and we set equal to the average rate of change, the negative 5. So negative 2x equals negative 8, x equals 4 would be the location for which the mean value theorem applies. And 4 is in between 2 and 6, so we're okay. Depending upon the complexity level of the question, you could have an equation that has multiple locations for where it's equal to this number. Only consider numbers that fit in the interval. So like let's say, for example, this is a quadratic. I got x equals 4 and x equals 9. 4 is great, 9 is outside the interval, so it would not count. So other times they'll come out and just blatantly tell you, using the mean value theorem, find where the instantaneous rate of change is equivalent to the average rate of change. So average rate of change, we would need to worry about the secant slope, so we need to know the function at the endpoints. So f of pi is sine of 3 pi, which is 0. F of 0 is sine of 0, which is also 0. So our average rate of change is going to come out to be 0 because we're going to get 0 minus 0 over pi minus 0. So the instantaneous rate of change is going to have to equal 0. So that's our derivative, which will get to be 3 cosine 3x equal to 0, which means cosine 3x is equal to 0. And based off the unit circle, our answers would be pi over 2 and 3 pi over 2. Now, depending upon the interval here, we might need to expand out and consider more coterminal angles. The interval is from 0 to pi, so we don't need to worry about any negative coterminal angles since it's only 3x, we'll just be dividing, but we should include some additional coterminals. So 5 pi over 2, 7 pi over 2. And a general rule of thumb would be if it's 3x, we want to have 3 sets of answers. So pi over 2 to 3 pi over 2 is one set from one rotation, and then 5 pi over 2, 7 pi over 2 is a second set, 9 pi and 11 pi is the third sets. Dividing each of those things by 3, we get pi over 6. We would get pi over 2. We get 5 pi over 6. We get 7 pi over 6. And right there we can stop. We didn't need anything else because now we're past our interval from 0 to pi. So the rest of those weren't important. It was only going to be these 3 locations for which the mean value theorem is applying. The instantaneous rate of change is equivalent to the average rate of change. So just watch out for that whenever there's a coefficient involving x. If it's like x over something, we probably don't need to include any coterminals, but just pay attention to the window. If it's like a negative, like negative pi to positive pi, we should have some negative coterminals in there. Just kind of depends how many. Just kind of list a couple of them out in both directions. Make sure that you have your cross off at the max point and cross off at the minimum point to ensure that you've done enough. All right, so here's a non-trig function. Same idea is going to apply though. So we're going to go ahead and take f of 3, which is the square root of negative 5 times 3 plus 15, which is 0. F of 1, which would be the square root of negative 5 times 1 plus 15, which is the square root of 10. So our average rate of change would be 0 minus root 10 over 3 minus 1, which is a negative root 10 over 2. Okay. So instantaneous rate of change, that's our derivative, where we want to think of this function as being raised to the 1/2 power. So we can apply our chain rule to this. So it'd be a 1/2 negative 5x plus 15 to the negative 1/2 times a negative 5 for the derivative of the inside. So this would yield us negative 5 over 2 square roots of negative 5x plus 15. Now, back when we just only did derivatives for units 2 and 3, I never really had you guys rewrite the negative exponents simply because it wasn't necessary. Here, when it comes to using the derivatives, we definitely need to always rewrite wherever possible because we're going to have to solve an equation here. Because this is going to have to equal the negative root 10 over 2. So we recognize the 2's would cancel each other. They're both in the denominator, so they're not relevant. Cross multiplying, we get and the negatives would also cancel each other. So we would get a negative 50x plus 150 inside the radical equals 5. Squaring both sides clears the radical. Negative 50x plus 150 equals 25. So negative 50x equals a negative 125, meaning x is a positive 2.5, which falls in between 1 and 3, so we're okay. It's entirely possible you might get questions here that are more obnoxious to solve out, in which case you'll be allowed to use a calculator. And then the key really is anytime you're trying to solve any sort of equation for when it's equal to something else, you just make it all equal to 0 and graph and zero across the x-axis. All right, now you might get these kind of questions in terms of a table. Because again, we're talking about average rate of change here, so that's again found from just doing a slope of a secant line. So this scenario is based off a hot air balloon being launched into the air with a human pilot. Twice differentiable function. That's important because it tells us it is continuous and it is differentiable. In fact, it's twice differentiable, meaning the second derivative also exists. H mile is the height measured in feet, t measured in minutes. The table below gives us certain height values at select times. So part A, from 5 to 15, must there be a time when the balloon is 50 feet in the air? Justify your answer. So part A is not mean value theorem. Part A is what's called the intermediate value theorem. Intermediate value theorem. Abbreviated as IVT. And what the intermediate value theorem talks about is if you have, again, the key is like mean value theorem, it has to be a continuous function. Because if you think about this, so if we have, for example, in this case, from 5 to 15, we've got a height of 40, and at 15 we have a height of 70. The question is, do we have to cross 50 at some point here? And the answer is yes, because assuming this function is continuous, which it is since it's twice differentiable, the only way to get from here 40 to here 70 is I have to cross 50 at some point. Now, whether it crosses a nice linear line like that, maybe it's more of a curve, maybe it's something truly bizarre and it crosses multiple times, regardless, it has to cross 50 because it's continuous. All right, so the answer would be quite simply yes. Because of the intermediate value theorem, we have to, since we're at 40, and 50 is in between 40 and 70, we have to cross. Part B, this is now talking about mean value theorem because we're talking about from 20 to 30 when the time t balloon's velocity is 1.5 feet per minute. I'll talk about a rate, it's talking about a derivative, and a derivative is the instantaneous rate of change comparing to the average rate of change. So we look at the interval from 20 to 30. We go, okay. So it's 80 minus 65 over 30 minus 20. We get 15 over 10, which is 1.5. So that's our average rate of change. There's our instantaneous rate of change. So the answer is yes, because of the mean value theorem. All right, so that's generally where a lot of times you will see intermediate value theorem kind of applied in connection with mean value theorem. They kind of go hand in hand together. All right, one last example. Here they're giving us function values at 1 and 3 because they're not giving us the original function, they're giving us the value of the derivative. And they want to know how many values of x in this open interval 1 to 3, meaning not including 1 and 3, will satisfy the conclusion of the mean value theorem for the closed interval. Okay, so we're given the derivative, and the derivative is a linear function multiplying with a trig function, sine. So the derivative exists everywhere. And there won't be a situation where the derivative does not exist, because it's not a tangent function which could be dividing or secant or anything like that. So we go ahead and find our average rate of change. So f of 3 is 3 over pi, f of 1 is also 3 over pi, and we get 0 for the average rate of change. So we want to know how many times does the instantaneous rate of change, this derivative here, equal to 0. So what you're going to do is you're going to go ahead and graph this. So you can take out your calculator, you're going to go and graph x minus 2 in parentheses sine of 2 pi x. You're going to make sure you're in radians mode, and you're going to change your window. So your window here, depending upon the problem, you're going to want to adjust the x min, x max, y min, and y max. X min and x max should be based off the interval. X min's got to be 1, x max has got to be 3. That's the interval we want to worry about. So we don't want to care about what's happening before or after, only from 1 to 3. And as far as the y min and y max goes, it depends on what I'm doing. If I'm trying to verify it's crossing the x-axis or touching the x-axis, which is what we need to show because it's equaling 0 here, I generally make the y min and y max relatively small, close together, -1 to 1. This will make it easier to see whether or not I'm actually hitting the axis or I'm just kind of barely grazing it. Because at some resolutions, you might have a graph that kind of looks like this. You're not quite sure what's happening there, but when you zoom in on that region, you see that it's actually crossing and coming back up. Okay, so certain graphs you need to watch out for that. So that's why I generally zoom the y min and y max in a lot if I'm caring about where I'm crossing. If I'm caring about the locations of the y's, then I probably leave it as -10 to 10 and just kind of adjust it from there. All right, so we go ahead and graph this, and your screen should give you something that looks like this. So there's 1, there's 3, obviously there's 2 in the middle. Your graph is starting at 1, going down, kind of coming up, down, some version of that. It's not really scaled properly, but that's what it's showing us. And you should be seeing when you're looking at this, there are a total of 3 times, right here, and right here, 3 times, where the derivative is equal to the average rate of change. The fact that it's 0 at 1 and 3 is not relevant because say how many values of x in the open interval satisfy. So all we care about is that it's continuous on the close, so 1 and 3 exists, but it's the open interval we're looking at. So we're not caring that it's 0 at 1 and 3, only everywhere in between. All right, so that's our mean value theorem. Now you notice a lot of the questions are talking about the average rate of change being 0 and solving the derivative based off that. That's an important concept here with the calculus. We're going to explore that a lot more in 5.2 with the idea of critical points. So I'll see you next time with that video.